Welcome to the first day of our new unit on magnetism. What I will attempt to do this unit is to put together readings from your textbook, online simulations, YouTube videos, and make a coherent unit out of it. And what you'll have at the end of today and at the end of other days in the unit is you'll have a practice set of questions that come from the materials that you would have looked at. So let's look at this first page here. And this actually connects to something that you did earlier this year. So this is not magnetism per se. This is electrostatics and the study of electric field lines. And we did a lot of this in our electrostatics unit. So I just copied and pasted this from something in the past, but I would have you draw the electric field lines. Even there, during the test, I always included the hint. The field lines are drawn in a way that a positive test charge would react in the environment. So what we did at the time is we put a little positive test charge, say here, and then we'd say, okay, well, if that's a positive charge, which way would it move? We'd say, well, it would be repelled by the other positive charge, and it would be attracted towards the negative charge. So then we drew a field line like that. And what if we put a positive test charge here? What would happen to it? Well, it's so close to this isolated positive charge that it would greatly repel, and then it would get attracted to the negative. And a positive test charge here would quickly and greatly repel, and then it would get attracted over here. So we came to draw our electric field lines, something like this. Now what I'm doing here, because we're not doing the electrostatics unit, so we've had some distance from that, the hint I'm providing is that, remember these field lines, see if I can switch the color up, these field lines point towards the negative charge. So I'm even being more explicit when I have you do this question on electric field lines. And so you might say, well, why are we doing electric field lines if we're studying magnetism? And that's because both electrostatics and magnets are action at a distance, and so they're very much related. And so we're building that connection right now by my going back into electrostatics and have you answer a question like this. Okay, I way over talked that one, I think. So expect to have that question asked and to need to know how to respond to it. Then we do get into the magnets part of it. So you're going to be reading from the book, and this is just one image taken from probably 3 pages that you're going to be reading, and here we are again talking about magnetic fields. Okay, so what they offer here, and just to give you a preview, this is also what you're going to see in the online simulation, and I believe it appears in the video as well. I'm going to have you look at today. So we start with a bar magnet, which you probably have seen before, and of course if we were in class we'd be playing with these. And you put them over iron filings. So iron filings are these teeny little slivers of iron, but they react even at a distance from the magnet. So they respond to the magnet because the magnet that I've outlined in red, that has an aura around it, and that aura is the magnetic field. And the iron filings respond to that in a way that interestingly looks very much like the field lines for an electrostatic field. And so what you will learn is that if you draw the field lines around a magnet, the field lines move towards the South Pole. So these are just physical iron filings, so you don't get to see an arrow on each of these points. But if we were to accept the rule that magnetic field lines point in the direction of south, we would put a small test point here, if you will, and the south would get sort of readily repelled by the north, but then ultimately it would point towards the south. And so you would start to see field lines that looked like this. And again, I want you to make the connection between the look of the magnetic field lines around a magnet and the look of the electric field lines around a positive and negative charge. Okay, so that's part of your reading. And then we go to, whoops, let's go to page 3, an online simulation. Now, note that this magnet is flipped from the ones that appear in my previous materials. So here we have the south end of the magnet to the left. So that's not how it appeared on the other page, but the concepts are the same, and technically the results will be the same. It's just going to look a little bit flipped to you. So what you can do in the simulation is and this is just an image, so I can't actually do it, but in the simulation you can take this compass and you can take this compass and you can drag it around the magnet. And what's going to happen is the compass, we think of it as pointing, our compasses point towards north, right? That's what we learn in scouts, if you will. And yet from a science standpoint, we learn that the arrow is pointing towards the south pole of a magnet. So that's a little bit reverse of what we think of. So again, in the practical world, in the woods, we say, oh, our compass points north. But from a laboratory science standpoint and the way conventions were established, that compass is pointing towards the south pole of a magnet. So as you move that compass around in here, what you should see is that needle will always be changing. And so you can think of this compass as just a blown up version of each of these small flecks down here of establishing the direction of the field. And so what we see is, like we drew up on this other page for the magnetic field lines, if I can get there moderately quickly, what we see in the pattern here is that these field lines are always pointing towards the south pole. And similarly, if we took a look at a little test point right here, it immediately gets rejected by the north pole, if you will, and then it gets drawn / attracted towards the south pole. So the look is very similar, building a connection between electric field lines of electrostatics and magnetic field lines of magnets. So that's a simulation you'll play with. And then lastly is a video, and boy, there was a lot packed in this video, and some of it goes beyond what we're going to need. This is just a screenshot of one of my favorite parts of the video, and this is where the host, this is a magnet up here, and the host shows how you can induce magnetism in certain objects. So this is an iron paper clip, and it's been brought towards a powerful magnet. And so that through ways that he describes, it ends up aligning what are called domains in the paperclip, and the paperclip can then become a magnet and get attracted towards this magnet. So even though this is just a string right here, and you might think that the paperclip might just fall to the ground, it's actually been magnetized, if you will, and it gets attracted towards this fixed magnet on the wood. So this host talks about a variety of properties of magnets, talks about the periodic table from chemistry a little bit and what elements can be magnetized. And so I think there's a lot in there, but it's a good video, so I'll have you watch that as well. And then when you're done with those things in Classroom, you're going to see something called Practice Set Day 1. And it's got a variety of questions, things I've talked about here, things from the video, things from your textbook reading. So respond to those and submit those on Classroom. Okay, that's it for day 1. Thank you.